Oh my God, don't.
Yeah,
Okay. Now you are going live. So, hello everyone. I'm so happy to. You are so happy to have you all today. Welcome to this new meetup organized by PyLadies Tunis. So this is an overview about our PyLadies chapter. So you are a human who love programming with Python. PyLadies Tunis is part of the global community PyLadies Global. This is our team. I'm Munib Eid. I'm so basically engineering statistics and data analysis, and I'm working now as a business intelligence consultant.
sorry,
Uh,
Mona, could you please share the presentation?
okay, you are not sharing my screen.
Yeah,
It's fine. Just 1 second. Uh, okay, I think now should be okay. Okay, if you could just confirm to me that it's okay, Amal.
yeah, just one minute.
Good. Amal, great. Yeah, this is our team. So along with Amalit Lili, who's also the co-founder of PyLadies Tunis, and she's a data science engineer, and with Hediat Nani, who is a postdoctoral fellow at Pasteur Institute of Tunis. You are part of a global community which focuses on helping more women become active participants in the Python open source community. So you help more women become active participants from our side in this community, and you promote mainly the gender diversity in the Python community. You organize like education and conferences, sorry, events and about mainly related to Python. Okay, so today this is just an overview of the machine learning in the cloud series that you started organizing. Before you covered meetups about MLOps, Emira covered how about the tools and the steps to scale a machine learning model. And the second one, the second meetup of this series. With Carla, we learned about how to build and train and deploy machine learning model now on AWS. If you have missed these meetups, it's okay. You can like have a review at the recording videos shared on our YouTube channel. So the link will be shared in the chat. What about our next meetup? So for tomorrow, the first one at 10 a.m. Tunis time will host Hafid, and he will animate a workshop about data analysis with NumPy and Pandas in Python, these libraries. Then the evening will be pleased to be hosting Laura also. So she will cover a meetup about how to create a dashboard with the Dash library. So make sure to be part, to join our meetup group, and to follow us on social media to be notified about our next events. Yeah, what about today? Today you are so pleased to be hosting Marc Cohen, who is a software engineer at Google, and he will cover the deployment of machine learning models at Google and Vertex AI system services. Marc Cohen is a software engineer working on Google's developer relations team in London. It's okay. So I'm sorry about this mistake. Okay. So before joining Google, Marc spent 30 years building products and managing engineering teams in the telecom industry. You are so pleased to be hosting him, and I'm sure we learned a lot from him today. Before you start, so if anyone has a question, please don't hesitate to leave your question in the chat. Thank you all for attending this session and for being here. I will let now Marc start sharing his screen. Okay, let me just stop sharing my screen.
Okay, thank you, Mona, for that nice introduction, and thank all of you for joining me tonight. I'm really happy to be here, and thanks for inviting me. So I have two cats with me here, and they will probably jump up on the desk at some point. They like to wait until the worst possible time, and then they jump up. So they do. They'll be our guest stars today. What I would like to do today is kind of give all of you an overview of something called Vertex AI, which is a new offering that Google's providing to make it easier to work with machine learning and other data science topics in the cloud, in the Google Cloud. I'm going to divide it up into kind of a talk portion and then a lab portion. So I think I'll do probably 40 minutes each, and I'll put a 10-minute break in the middle. So if you want to hang on for the lab, that'll come second. All of the slides are available right now online. I've just put them into the chat, although it says private chat, so I don't know if streamers will see that or not. When I share the slides, you'll see the link as well. And I also wanted to say, if you have questions at any time, please feel free to stop me, message me in any way, chat, anything you would like. And with that, I will go ahead and share my slides.
Yes, that's fine.
Okay. So yeah, if any time you can't see or hear me, go ahead or if you can't see my slides, go ahead and just put a comment in the chat to me or let me know online. So all the slides, as I mentioned, are available online. The URL is quite simple. It's mco, which is the short name I use for myself. mco is in Marc Cohen. So mco.fyi/ds for data science. So feel free to take a look at those now as we're working through them or later. Here's an agenda for the talk portion. What I'd like to do is start by giving all of you a quick orientation, kind of a quick tour of Google Cloud. Hoping it'll be new for some of you. If you're already familiar with Google Cloud, I hope it's not too repetitive. Then I want to talk about ML ops and what that means to me, and then talk about two different products, the Bigquery product and Vertex AI. So let's jump into it. First, to start with Google Cloud, I like to go back a step, and I like to talk about a little bit of philosophy. And what I mean by that is whenever I do anything with data science, or actually if I put it in the context of an application, let's say I write a web app or some kind of application I want to share, there are a lot of things I have to think about that I don't want to worry about. Or at least I used to have to think about these things, especially if I go back in history. I used to have to worry about provisioning hardware, installing software, making sure I had all the right security patches. How is my service going to scale? How will I deal with failures? It's a lot of stuff that I had to think about. And really what I wanted to think about was just one thing. I wanted to solve my problem. And as a result, I had to spend a lot of time really worrying about stuff I didn't care about that much. And that's kind of where I come at cloud, right? So everybody has their own way of defining what cloud means to them. And there are certainly many different dimensions you could talk about. But for me, what I like most, what excites me most about cloud is that it enables me to get things done using someone else's computers. So, and what that means indirectly is somebody else is worrying about all that stuff that I said I don't want to think about, like the maintenance and the administration and the networking and all that stuff. So to me, that's, as a developer, as a coder, that's the big benefit of working in the cloud. And what we're going to get to in the next section of the talk, after we do this quick overview, is what that means from the data science context. So we've seen how that's played out over the last 20 years with application development. And really what we want to do next is apply that same sort of ease of use to the machine learning and data science world. But before we go there, I wanted to just give you a quick hands-on kind of feeling for what Google Cloud looks like. So there's 3 ways to access Google Cloud: the console, the command line, and the programmatic, the APIs. So starting with the console, you can click here on this link if you look at the actual slides, and it will take you to the Google Cloud console. And this is kind of like the home base for everything you do in Google Cloud. You will typically select a project from this pull-down menu, and you can sort of get a view. It's sort of like a dashboard view of everything you're doing. But then typically you'll want to interact with a particular service, and this navigation, actually I should make this a little bit bigger. This navigation menu on the upper left is where you can access all of the different services. So for example, if I wanted to create a virtual machine, I would click Compute Engine, and I would have all of the interface I needed to create a computer in the cloud. And of course, it's slower than usual because I'm giving a demo, but I'm in the wrong project to show you what I wanted to show you. So let me go to a different project, and by that I'm just showing you how easy it is to switch projects. And a project is nothing more than a collection of resources in the cloud. So now that I'm in this other project, I can say create instance. You may not have noticed it, but in the other project, I didn't have permission to create a virtual machine. So that's why I switched. But I'll name the instance. I'll say where I want to create it. And then I have all these different computing choices: what series, what machine type, what configuration, how much memory, all different types of capacity options and stuff like that. And this isn't a talk about compute engines, so I'm not going to spend much more time on this, but I just wanted to show you what the interaction with the console looks like. So I'm creating a virtual machine. And one of the nice things is it gives me this little SSH button. And once the machine is created, I can just click that, and this instance is stopped. So I'm waiting for this instance, and I don't want to wait 30 seconds, but it's actually pretty quick. It's on that order. And once it's running, I can click that SSH button, and it brings up a browser window where I can just log right into the machine. Oh, it's already done. So I can click that SSH button now. And as mentioned, I get a browser window. Do you want to connect? The first time you connect, it's transferring SSH keys and kind of getting stuff initialized. So it tends to be a little bit slower, but the second and subsequent times you connect, things are much snappier. Establishing connection. Okay, there we are. We're logged in. So we just created a server, and yeah, we logged into it, and we didn't have to download anything. We didn't have to install anything. So I think ease of use is one of the things we're really proud of with our products. And this was just one quick look at a service, namely Compute Engine. But let's go back. And so that's a look at the Cloud Console. The other modality is the command line. Now, the command line is, as you would expect, it's a command line tool. And pretty much everything you can do with the console, you can do from the command line. There's a nice capability that you should know about if you use Google Cloud at all. And that is that if you go to the console, so I'm just going to go right back to that console page, there's a nice little button here called Activate Cloud Shell. And what that does is it gives me access to a command line processor running in the cloud. And the cool thing about this is you don't need to have signed up for anything. You don't have to give a credit card to Google. It's totally free. And you will see in a minute, it's provisioning a machine. So it's kind of doing behind the scenes what I just did with Compute Engine. It's creating a relatively small, not particularly powerful machine, but enough to give you a shell that you can do some interesting things with. And so there it is. I'm running. And again, it'll be a little quicker the next time I do it. I can also open a code editor in the same window. And it's a really easy, convenient fairly well-connected way of doing work in the cloud where, so here's what the editor looks like. It looks like a typical IDE, VS Code type implementation, again, running in the cloud. And I can go back and forth between the editor and the terminal. And the modality I was really talking about is this gcloud command. And so if you run that, you'll get all the different options. And it goes on forever because there's a lot you can do. But for example, I could say gcloud compute, and that tells the command I'm talking about, compute engine, which is the service I just used earlier to create a virtual machine. And I think I say create invalid choice, and it tells me what the other options are. So gcloud compute, I think it's instances. It doesn't show it there because I didn't ask. It's trying to be helpful and saying maybe you meant this, but you can give the help command to get all the details. But the one I wanted is gcloud compute instance or instances, and then I can create, add, remove, things like that. So this is probably why for something like this, I would tend to prefer the web interface. But if I wanted to automate this with a shell script or something like that, this is quite nice. So gcloud compute instances create. There's a million arguments I can give, but I would give it enough, the minimum that I needed to customize it. And then it would do exactly what you saw being done from the web. So I'm kind of bundling a few things in here. The main point was to show that you can do everything from the command line using gcloud, but in the vehicle I've used to show you that is this cloud shell hosted in the right on the console. So that's a nice thing to know about as well. And then the third kind of modality is Google APIs. So everything you can do with the console and everything you can do with the command line tool, you can do with our cloud client libraries. So that gives you another whole level of service. And of course, being Python people, you'll be happy to know we have first class Python client library, but we also support all these other languages, which probably may not be able to read unless I blow this up a bit, but it's the Go language, Java, Node.js, Python, Ruby, PHP, C#, and C++. And for some reason, JavaScript is not mentioned, but I think that's presumed in the Node.js camp. But anyway, those are all the client libraries that you can use to do pretty much anything you want to do with Google Cloud. So that's all very general, just kind of foundational aspects of using Google Cloud. Any questions on any of that so far? Don't know if the chat will come through to me or not, but I'm not seeing it.
So yeah, you can see the chat from the comments. You see, you have the comments section. Yeah, from here, so we'll receive the questions. But for now, so there is no question. It looks like it's fine.
Got it.
Yeah.
Okay, I'm seeing the questions now. I was in the wrong tab. Thank you. Okay, so that's I don't know, 8 minutes on what Google Cloud is, and hopefully gives you a little bit of a sense for how it feels to operate with our cloud. Next up, I want to talk about ML Ops, because that's really, I know, the focus of this series. And I was talking earlier about how at least when I used to pre-cloud build apps, there were all those things I didn't want to think about. And you can sort of draw an analogy with the machine learning problem, or the challenge of deploying machine learning systems. And a different way of framing it, but similar, is to observe that launching a machine learning app is easy, but then keeping it alive and running and having all these great engineered attributes is actually quite hard. If you're used to this experience where you get a model to work, it does something interesting, you get very excited. The distance from that prototype to actually having a production quality service that's a big distance. In fact, what we found at Google is that by looking at the source code in our models, the actual machine learning code itself is only 5% on average of the full amount of code you need to write in order to, well, I won't say that you need to write, but that you need to use in order to deploy a scalable, high quality production service. You have to worry about all these other things. And so this is starting to look like my things I don't want to have to worry about list, right? I mean, some of these things I might be a data engineer and I do want to think about data collection, or I do want to think about data extraction, but I might not want to think about all of these things. So it would be really nice if I had a toolkit that helped me, or a service, and especially a service in the cloud, so I knew it had all these great attributes to take care of some of those requirements. This is a little bit of repetition, but some of the things you do, I'm sure you're aware of this, is cleaning the data, processing it at scale, scaling out your training. You might have a big enough model, you need to use lots of machines, and how do you gracefully grow and shrink the processors when you need it. Monitoring your model, let's say you do put it into production and it's working great. How do you know 3 months from now it's still kind of giving you the quality predictions you expect of your model? And of course, you want to manage the access to your model and your data and all the resources that go into your service. So there's really lots to think about. And at Google, we've been deploying models with, some of them with billions of users a day, with a lot of technology that we've built internally. And what we're trying to do with Vertex is to take some of the capabilities, some of the code, and a lot of the learning, a lot of the lessons, to make it easier for people other than Google, external developers, to be able to have the same capabilities that we've been working on. And this paper, by the way, I don't know if it's clickable. No, it's not. You can search for this online, but it's a nice paper to read because it basically has it sort of boils down all of the lessons that we've learned over the last kind of decade and a half of deploying well-engineered machine learning services. This is a quote from, "On any given day, there's thousands of pipelines running, processing exabytes of data and producing tens of thousands of models, which in turn are doing hundreds of millions of inferences per second." And so that gives you a sense of the kind of scale these services have had to achieve. And so that's really informed the services I'm going to talk about. And they're really, as I said at the beginning, there are two different kind of groups of services I'll cover. One is Bigquery, and the other is Vertex AI. So let's start with Bigquery. Bigquery is a data warehouse. So it's a way to store your data in the cloud. It's got some really powerful and unique capabilities, one of which is just its raw speed. And I'll show you an example of that. But you can do queries on really big data faster than you could sort of believe. You'll see what I mean. But it gives you a SQL interface, standard SQL, and everything is automatically scaled to do the queries that you need to carry them out very rapidly, and everything's encrypted and highly available, and all the sort of things you would want to get from a high-end service like this. So let's actually look at Bigquery. Stop talking about it and show it to you. So just like everything else in Google Cloud, you can navigate to Bigquery through this upper left navigation menu. And one thing that's sort of fun to do is, so what you're looking at here is there's a bunch of different data sets on the left, and then there's a query window on the right where you can write SQL and generate the output and examine it and so on. And one of the nice things to just kind of get started with this is called Bigquery public data. So these are data sets that everyone can access, and there's all kinds of interesting things in here, from crime data to medical data. There's a ton of COVID stuff here. crypto data, cryptocurrency data. There's data sets about GitHub, which people have used to analyze like things like, what are the most popular programming languages and how has that trended over time, all the way to what's better, tabs or spaces. I think we all know it's spaces, but there's lots of interesting, fun things you can do. I'm just kidding about the spaces. I'm kidding that that's the answer, but I'm not kidding that I prefer that. But anyway, the data set I want to show you today is called Wikipedia. So this has the page view logs of every Wikipedia access year by year since 2015. Now, what that means, you can click on the data set and you can get a view of what it's all about. The schema for this data set is very simple. It's a timestamp, which language wiki it came from, the title of the article, and the number of views for that hour. And so that's per article. So you're getting, this is 1.9 terabytes. So this is almost 2 terabytes for all of 2021. And you're just getting one message for literally every single time. Well, it's not one message for every access. It's aggregated per hour. So you're getting a count of how many times every article that was accessed in a given hour. So hopefully that's clear. Let's query that data. So I've got a saved query here. And let's see, I'll do cities. So I can open the query in the editor, and let's slide this down. And let me make this bigger for you folks too, so you can see it better. So here's a SQL query. It's saying select the title and the sum of the views from the public data set for 2020. Let's make that 2021, make it a little more up to date, where the title contains this regular expression, London, Paris, New York. And I'm going to change this to be more local. So I'll do T, uppercase and lowercase t, and Tunisia. So I'm looking for the most popular articles with the title that contain the word Tunisia with either an uppercase or a lowercase t. And then I'm going to group them by the title and order them by the number of views. So let's run that query and see how long it takes. Now, what's one of the things to sort of note about this is not just, first of all, this is scanning every row in that data set. And I'll tell you how many rows that means, but it's looking at every row literally in a very big data set. And it's not just looking at every row, but it's running a regular expression on every row, which is actually pretty expensive operation to do. And this is, granted, this is a pretty trivial regular expression, but still it processed, it shows here 667 gigabytes in 10 seconds. So 2/3 of a terabyte, it just queried in 10 seconds, and it ran a regular expression on every single row. And if you're curious about the results, you can see Tunisia, kind of not surprisingly, was the #1 article that contained the name Tunisia. The national football team was #1, Tunisia Revolution campaign, Tunisia at the 2020 Summer Olympics. Some interesting things you can find out about sort of the culture by looking at these logs, and being able to process them that fast is it really enables you to kind of increase the speed at which you're iterating, that you're finding out insights about your data. And one thing I want to say is that there's no index in this database. This is kind of what's really one of the special things about BigQuery. In a traditional relational database, let's say, if you wanted to do a query like this with a reasonable response time, you would create an index based on the field that you wanted to drive, that you wanted to focus your query on. And you don't need to do that with BigQuery because it's distributing the processing over lots of computers in parallel. There's no indexing necessary. And as a result, in the traditional world, you have to know ahead of time what you want to query on and create an index for it. And this, again, makes this faster to iterate because you don't have to figure out ahead of time what fields you want to query. You can just dynamically change the query and not worry whether there's an index or not. From here, you can do interesting things like create graphs and push the data to a service called Data Studio, which is kind of a drag and drop dashboard. I won't go into that, but a little bit more details on the execution. So it was 667 gigabytes in 10 seconds. But as I said there, it ran a regular expression on every row, but I didn't tell you how many rows. And this is telling us it was 16 billion rows. So 16 billion regular expressions in 10 seconds. Pretty good for me, at least. If you were to try to do this not in the cloud, let's imagine you said, I'm going to go buy as many disks and computers as I need to process. In this example, it was 2 terabytes in 15 seconds. We saw it was like two-thirds of a terabyte in 10 seconds, I think. But anyway, this is close enough. In order to do that using like current hardware specs, and this is a very rough calculation, so don't quote me on this, but using very simple back of the envelope math, you would need 1,000 disks and 3,000 processors or 3,000 cores to perform the kind of query in the amount of time I just did. And so, we're not doing any magic beyond the fact that we're throwing a lot of hardware at these queries. And so the way I like to think about it is when you click the Run Query button with BigQuery, Google is allocating on the order of 1,000 disks and 3,000 processors for you for 10 seconds. And so if we go back to this idea of like, I don't want to think about the administration stuff, this is a perfect example of what I mean. I don't want to buy 1,000 disks or 3,000 processors. I don't want to figure out how to network them together. I don't want to figure out how to allocate them for 10 seconds. I don't want to pay for them except for the 10 seconds that I'm using them. So this is a great example of where I can just focus on the problem, the question I'm trying to pose and how to get the data, the insight I want out of the data. And I'm happy to let Google take care of all the stuff I don't actually care about. There is a nice feature in BigQuery called Bigquery Ml, which provides you the ability to use standard SQL to actually train and serve models. It may not be the right answer for everything, but if you already have a whole bunch of data in BigQuery and you just want to train a model, instead of transferring all that data to some other tool and building the model, you can actually build the model natively. And the great thing is you don't have to move any data. And the bigger the data is, the more hassle it is to move it around. So just to give you a sense of what's possible with BigQuery ML, these are all the algorithms that we currently support. So hopefully some of your favorites are on here, and it's continually evolving. So we're hoping to add more and more capabilities. So that's BigQuery in a nutshell. Don't see which type of model we can find in BigQuery ML. So I think that last slide might cover that. You have a bunch of classification methods, a bunch of regression algorithms, then k-mean clustering, recommendation, autoencoders, lots of different algorithms there for you to use. And you can also serve the models in BigQuery. So once you train the model, you can then actually send requests through BigQuery to make predictions. So from there, I want to take a step back and talk about Vertex AI, which is a different system altogether from BigQuery, although they play nicely together. So Vertex AI is a managed platform to make life easier for machine learning people and data science people in general. It has lots of capabilities, which I'll go through. This is kind of a salesy, marketing-ish slide, but really what we're trying to do is to come up with a central means of controlling the entire journey that you would take through building ML systems and services. So ingesting data, analyzing it, transforming it, training, etc. Every step along the way, we want to kind of make it easy for you to kind of go through this journey of productionizing machine learning. The other thing we've tried to do is to come up with services that are very versatile relative to your expertise with machine learning. So you can do things like build your own custom models with PyTorch or TensorFlow, and really really kind of take ownership of the details of your machine learning. Or you might be someone who just wants to use the technology but doesn't necessarily care about all the details of a given model. And if you have a task that fits an existing model, what we've done is we've made pre-trained models available for you to call with a simple programming interface. For example, we have natural language processing sentiment analysis models. We have image classification models. We have object tracking models. We have video, finding objects within video, like this GIF on the left is showing. Probably forgetting others. We have AutoML, which is our technology for kind of finding the right model for a given set of input. Typically, that's done with structured tabular data. Anyway, we've got all of these capabilities. And so if you're someone who just has heard about ML and one of these models that we have suits your needs, you don't have to care about the details. You can just send us Python requests and you can use the model freely. But if you're more of an engineer who wants to really, get your hands dirty, you can do that too. So the first capability I wanted to tell you now I'll just kind of walk through the capabilities. And by the way, just so you can get a sense of what it sort of looks like to use Vertex. Let me go back to the BigQuery window. So I'm just going to navigate over to Vertex AI. And yeah, I don't care about saving that query. And I get a dashboard. Let me go to a different project, AutoML demo. And I get this dashboard with some high-level information. And then I can select different capabilities that are part of the Vertex AI service. So the one I'm going to talk about right now is data sets. And this enables you to operate on your data sets. But in addition to that, it lets you store them in a central place and share them with your team and so on. I'll show you what that looks like for a sample data set that I've worked on. There's a data set here which has pediatric X-ray images. So this is used by radiologists to determine whether a child has pneumonia or not. And so it's a data set with 5,800 images, all labeled pneumonia or normal. As you can see, you can upload your imagery, and then you can actually see the images, individual images, and expand them and so on. You can edit the labels. You can upload fresh data and label it on your own. There's a lot you can do. You can get some analysis on the aggregate. characteristics, and you can import new data sets. I'm not allowed to import on this particular project, but yeah, I probably won't worry about that for now. But if you do go into the data sets and say create, it gives you options for these different types of data. So image data, tabular data, text data, and video. You don't have to put your data on in the Vertex managed data sets, but it makes things go a little bit easier for some of the downstream services. So that is managed data sets. Feature store is kind of for features what the managed data sets is for data. So you can engineer features, you can process your data into these independent units, if you will, and then you can share the features themselves independent of the data sets. And you can like train models based on the feature values. You can do predictions in real time based on feature values. It kind of gives you a higher level of abstraction at the feature level rather than the lower data set level. We have very nice integration with notebooks. I can show you if you're a Jupyter Notebook fan. I'm just checking my time here. I think I started about 10 of and 10 after, and it's almost 40 minutes now. So I think I may just keep going a little bit over on this section, and then I'll give you a 10-minute break. But if I go to Workbench, that is kind of the notebook, the environment for using notebooks. So you would typically click on Manage Notebooks, and you could say New Notebook. Let's go back to my other project because I'm quite limited in the one I'm working with. Okay, Manage Notebooks. These are very new, actually. They just were announced at an event we had about a month ago. So I'll say New Notebook, and I give it a name, a region, and create. I didn't show advanced settings, but I can configure. Sorry, I didn't show you that, but I can configure the hardware for the service, for the kernel, they call it in Jupyter, which is kind of backing up the notebook. So I can allocate very high-end hardware configurations if I'm going to be doing something really compute intensive, for example. But this will create the notebook for me, and eventually I'll get this Open Jupyter Lab button, which will open Jupyter Lab at some point. Sorry, this is not as snappy as I would like it to be. I think this one was, yeah, it was stopped. So it's restarting this. I should have had one of these like ready to go. I'll leave this tab open. Okay, so the notebook I just created is now ready to go. And that's a one-time thing when you're working with a notebook. You don't have to keep doing that. And I'll try this one. And I think we'll come back to this because it's either not working or I'm not happy with how long it's taking. But I'll leave that tab running. In that environment, you get a full Jupyter Lab. It's kind of like an IDE. It's like an integrated development environment for notebooks. So it's quite convenient. It's all managed by Google, so you don't have to worry about installing anything. It comes with all the stuff you would want: NumPy, SciPy, scikit-learn, TensorFlow, PyTorch, Keras, all the stuff you would ever want for doing data science. And it's really integrated with the rest of Google Cloud. So for example, let's say you wanted to train a model and the model is not in a managed data set. It's in a cloud storage bucket, which is like S3 if you're an Amazon person. Maybe it's billions of rows. Because you're working on a notebook that's running inside Google's cloud, it's going to have access to this amazing network that we have between our data centers, and you're going to be able to read that data into pandas or wherever very, very fast. So it's got very good integration with Google Cloud. Nice integration with BigQuery, by the way. Scalable, and it has really good Git integration, and that's really useful because if you've ever tried to work with notebooks at a source code level, it's a giant JSON file, and it's sometimes hard to do code reviews and things like that. And this tool abstracts a lot of that and gives you the ability to do Git operations where you're sort of like you're looking at the notebook, not the representation of the notebook. You have access, obviously, to lots of model training capabilities. And if you wanted to see where that lives in Vertex, you'd come down here to training. And you can say, I want to create a training job. And you can say whether you want custom, that's your own model, where you give us a bunch of code and we build it, we train it for you. Or you can say AutoML, where we just take the input and we find the best algorithm for you. And so, yeah, you can train the model, and it will do that asynchronously. So it'll say, okay, we'll do it, and it'll kind of go off and work on it. It could take a while because obviously training, especially a big model, can take a long time. And you'll get notified when it's finished, and then you'll, like this one here, you'll know that the job's done, and you can examine some aspects, and you can even test it through this this web interface. So that's training. And then we have this notion called, I mentioned you can do custom training as well. We have this notion called endpoints. And what an endpoint is kind of putting a face on your model. So it's making your model accessible to the outside world. And it might not at first be obvious why you would want an endpoint. Like, why wouldn't you make the model the thing that people start making requests of? And the reason is sometimes it's useful to have an extra level of indirection there. So for example, you might have two versions of a model, and you want to let requests go to both of them in a round robin fashion and see which one performs better or how they differ. So that would be sort of an A/B test scenario. Another possibility would be maybe you have a new version of the model, but you want to introduce it incrementally, where just like 5% of your community, your user community, sees that model, and then you can tell how it's doing without exposing your entire customer base to something that's not as well known as you would like it to be. So you can do that with this notion of endpoints. You create an endpoint, you point it to one or more models, and then you can do load balancing or versioning to define how you want the traffic to flow through to that model. And let's see what else. We have pipelines. That's a way of kind of building reproducible workflows for processing data. And that can include a lot of the things we already talked about gathering data, transforming it, training it, making it accessible to an endpoint, and testing it. So that's powerful, and that's integrated with everything else. And you can customize that with your own code, as well as use existing pipeline components that are provided by Google. There's a nice code lab here, by the way, if you want to find out more about, dive a little bit deeper into Vertex pipelines. Model monitoring is this idea that you'd like to keep an eye on your model after you deploy it and make sure it's behaving well over time. And the way this works is you tell the model, it's sort of the endpoint model combination, that you have certain thresholds that you want it to watch. And the thresholds can be either on a per prediction basis or even on a feature basis. And what I mean by feature basis is we have this idea of explainable AI, where for tabular models, we can tell you what the relative importance was of a given feature for a given prediction. So, like, let's imagine you're predicting whether something is a fraudulent transaction in a financial log. With explainable AI turned on, and when you send some data and ask a prediction to be made, you can get back both the prediction, the sort of the probability that it is or is not a fraudulent transaction, and you can also get back information about which of the features contributed most to that prediction. And what feature attribution monitoring does is you can set thresholds on the features, feature by feature, or on all of them together, and say anytime the importance drifts significantly, where significantly is you decide what the threshold should be, then you want to be notified. And essentially this will tell you that, over time, the user's country versus the user's age is becoming more important and the other one's becoming less important. So maybe I should rethink my model. Or it can tell you overall the accuracy of the probability seems to be changing, where actually that's not true. It's not that the accuracy, the input is changing. So the data you're seeing with the prediction stream is significantly changing, either with respect to time or with respect to the training data. You can fine tune it for both of those requests. That's kind of the end of my whirlwind tour of Vertex AI and a bit about how I think about MLOps and Google Cloud. I have some resources here where you can learn more. I'll leave that to you in the slides to check those out. There's this nice little resource here which I will highlight because it gives you on one page, it's kind of a cheat sheet. It's every Google Cloud service in 4 words or less. And my only advice about this would be, don't try to learn everything. Try to figure out what part of the cloud you're most interested in. And because you're Python people, and we're talking about machine learning, the piece that I focus most of my time on is data and analytics, AI and machine learning, which continues over here. I also have a place in my heart for web development and that sort of thing. So there's some other really great tools in there. But anyway, this will give you an overview. Again, the slides are mco.fyi/ds. And let's take a 10-minute break and then at about 11 after, let's do a lab together.
Yeah, that was good. Thank you so
Yeah.
much for this presentation. Okay. You have a question? Can you use pipeline with other machine learning tools like scikit-learn, right? Yeah.
No.
Yes. Yeah. So because the training abstraction can be any of the sort of training types that I talked about, where one option was custom training and one was AutoML. You can build a custom model that uses any framework you like, as long as you can containerize it into a Docker container. It can be trained as part of the pipeline. So not seeing any other questions, I think I'll take a break as well, along with you, and I'll be back in 10 minutes.
Okay.
It's fine. Thank you.
Mm.
Today,
So, hello again. I think we have a question.
Okay. I saw a couple of.
I think we have a question.
Sorry. Okay.
Yeah, Amal, yes, it's okay.
I saw some questions from Baru.
Yeah, right.
Can you advise for good architecture step-by-step for ML deployment in production? I want to automate all deployment processes. And I think that's a really good question, because what I think of Vertex AI as doing is giving you a lot of raw materials to make a process that is reproducible and shareable with your whole team and all that stuff. But it doesn't necessarily, do everything. It gives you abstractions, and you can build your process on top of it. So you can write scripts and programs, or processes, or I guess pipelines. The pipelines I showed you is the closest thing to giving you that automatic flow. But even that is not going to cover everything, right? You're still going to have some operational processes. So my take on this would be to try out Vertex and see how much it does for you and how you can envision putting all the pieces together. But I also feel like the industry is at this point where it's kind of building up the abstraction layers, and the having all the capabilities in one place is a really big step forward. But I feel like we're still missing some tool or some. It's almost like if you've used Terraform, we had all the capabilities to do what I did earlier, to create a virtual machine in the cloud and to create a cloud storage bucket. All the capabilities were there, but we needed something like Terraform to make it readily automatable. And you can make everything I've shown you automatable through Python programs or anything else. But I do still feel like we need a little bit higher level of abstraction. So I don't have a great answer for you other than that. I think this will go a long way towards giving you things you can tie together through programmatic use. Don't know how satisfying that was, but please feel free to add more clarification or any more questions at any time. I'm just going to share my screen now. And while we were on break, my notebook actually did get created. This is what it looks like when I click that Jupyter Lab button. I had to go through a little authentication dance, but this is what it looks like. So I'm now in that environment, and I have all these different types of notebooks. I can use TensorFlow 2, I can use R, PyTorch, PySpark, all these good things. And if I do create one of these, it will kind of give me an IDE, it gives me a brand new notebook, and I have Git integration here where I can clone a repository or commit changes to an existing notebook and so on. So it's a nice environment and nicely integrated with our cloud. So lab time. I have two labs here, and I was trying to figure out how to do this. The one lab is kind of a core machine learning lab where you build. I'll show you what it looks like. It takes you to a Colab notebook, which is yet another Google Jupyter Notebook service. I can tell you why we have two and so on. But what this looks like is you use Keras and TensorFlow to build a digit recognition model. And in the end, we can kind of interactively draw digits, and it'll give us the probability of what digit we're drawing. So it's kind of fun. It's very visual, but it actually doesn't use Vertex. And I can talk about as we go through how you would do some of these things in Vertex. But the other one is a forecasting lab, which uses a little bit of BigQuery, but several Vertex things to train the model and make predictions. But the problem with that is you'll have to have a cloud account to do it with me. So you'll have to either apply for the free trial or enter a credit card to actually be able to use it alongside me. Whereas with the Colab thing, you can just use it for free. There's no charge or anything like that. So I guess if we do the forecast one, I'll have to do it and you'll watch. Whereas if we do the ML Lab one, you can do it along with me. Maybe put in the comment which one you just type ML Lab or forecast so I can get a sense for which one people would prefer. And if you prefer the ML Lab just to be able to participate, get your hands on it, I can always come back. And there's a way I can give out free credits to the cloud. So if I come back, I can do a little more prep for that and give you some credits so that you won't need to enter a credit card or anything like that. So go ahead and make your votes, cast your votes. Not seeing any yet. I think we'll do the ML Lab. So let's jump into that. So what I'd like, those of you who would like to follow along with me, go ahead and visit mco.fyi/mllab. That's like one word, MLLAB. And what that should do, I think I had it open already, but I'll click on it just to show you what the experience will be like. It will bring you into Colab, and it should look like this. So let me make that bigger so you can see it well. So Colab is a hosted Jupyter Notebook environment, and it's really nice for just doing kind of experimentation. It's not going to be a production. It's not there to do production machine learning, but if you're kind of trying to do like a weekend project or just experiment, it's a really nice environment because it's sort of like Google Docs. It's the Google Docs of notebooks. In fact, you can save your notebooks in Google Docs or in GitHub. And like Google Docs, it's entirely free. And you can share the notebook with other people and so on. So it sort of looks like a Google Doc. In the upper right, you can leave comments, so you can click the share button and share a notebook with someone else. There's the share dialog. And you can say, I want a new notebook, and it'll give you a brand new notebook, just like creating a new Google Doc. There's also a bunch of notebooks. You can say open notebook, and you'll get a bunch of choices for some example notebooks. You can get anything from Google Drive or GitHub or upload something from your desktop. So that's just a little bit about Colab. And when you do run Colab, you're getting a machine automatically allocated for you to support your notebook, because Jupyter has this notion of a front end and a back end. And so the back end is getting dynamically created for you. It's just like the cloud shell thing. It's not the most powerful computer in the world, but it should be enough for you to be able to do some interesting experimentation. So with that, let's kind of jump into this lab. What we're going to want to do is turn on a GPU. So you have GPU support in Colab. So up here at the top, the menu bar, you'll see runtime. And if you click that and slide down to change runtime type, you can select under Hardware Accelerator, none GPU or TPU. And I'd like you to select GPU and then click Save. And what this will do is give you GPU support, Hardware Accelerator support when you train your model. So just to make sure I'm not picking up any stray, actually one step I should mention that I forgot to is save a copy of this notebook in Drive. So if you do that, that's under File, Save a Copy and Drive. You'll get a new copy of the notebook, and that will be your own private copy. You'll see that the title is now Copy of, just like if you're working with a Google Doc and you do make a copy in Drive, you'll get your own private copy, and now you can edit it and do anything you want to it, basically. So we'll work with that with your copy going forward. Now let's run some code. So the first thing we're going to do is install dependency. So click on the cell underneath install and imports.
I'm sorry to interrupt you. Could you please have this MLab this file now, to be able to go along the execution of the code with you? It's possible, or
the code view. Sorry, I think I misunderstood.
okay. So did you do you plan to to share with us the file to be able to execute the notebook with you?
Yes. What I wanted you to do is to go to this notebook and make a copy of it.
Yeah. Okay.
And so
Fine.
you'll have your own copy, but you won't actually see me change my copy.
Okay.
So anything we'll do, we'll kind of do it together. As you see me click on a cell, you'll run that same cell.
Okay.
So to go back to...
But you don't have the link, by the way, to the notebook,
Oh,
That's
yes,
why.
yes. It's,
Yeah,
sorry.
that was
That's
the
what
link
you're
that
asking.
I was asking about. It's fine.
Yeah, the
Yeah,
link
fine.
to the notebook is https://mco.fyi/mllab.
Okay, let me check. Yeah, so
I'm not sure if I can
fine.
put that in the comments, but
I will be able to put it. Thank you so much.
okay.
Yeah, you get it.
Thanks. So if you click on that link, you should see my notebook.
Thank you.
But you won't have permission to change anything. And I want you to have your own personal copy that you can do anything you want with. So then the next thing you'll do, once you get into my notebook, is you'll click File and then Save a Copy in Drive. And once you do that, you'll end up in a notebook that's named Copy of MLab. And once you're there, you'll set the hardware accelerator. I think it might be set by default to GPU, but you'll do that by clicking Runtime, Change Runtime, and make sure GPU is set, and then Save. And with that, you're ready to run code. So the first cell will be this install and imports. That will install lots of dependencies like NumPy and TensorFlow and Matplotlib and so on. After that, I'm just going to sort of walk through this step by step, but tell me if anyone feels like they're getting lost or something's not working for you through the comments, please. The first thing we're going to do is set some global parameters like the batch size. I haven't even told you what the data is, but we'll get to that in a minute. The number of epochs, so the number of sort of training rounds we're going to run, and the learning rate, which has to do with how fast we're going to try to zero in on the optimal model. So clicking that returns immediately because all we've done is set 3 variables. Now let's look at the data. And the data that we're going to play with is called MNIST. And I suspect many of you are familiar with this because it's a kind of a traditional data set for doing visual recognition problems. It's a large collection. I think it's 60,000 handwritten digits, and it's used to try to digitally figure out which digit was depicted in a given bitmap. So we're going to load that data using TFDS, that's a TensorFlow method for loading some pre-packaged data sets into these variables. So we're going to call it DS and DSInfo. DSInfo is sort of metadata about the data set. So let's run that. And you can see it's going to actually do a quick download. And it shows you a sample of what these bitmaps look like. And they're magnified so you can see the graininess, but they're actually quite small. And you can get a sense that these are actual human scratched digits. Now, let's see, I'm forgetting what this step is doing. Oh, that's the output of the metadata, sorry. So it's telling you the name of the data set, the source of the data came from this Jan LeCun's website, how big it is, and so on. So we've got this data loaded up, and we can actually look at these individual bitmaps. We need some utility functions that are going to make it easier for us to operate on the data. And so I've hidden these cells because they're not really central to what we're going to try to focus on. But if you want to, you can just click Show Code, and you can see what these are doing. They're not particularly interesting, but they're just making it easier for us. Actually, they're making it easier for us to do some of the operations we're going to do downstream. If you right-click on the right-hand side, by the way, that closes the cell. So what I'd like you to do is just run these utility cells one after another. Data processing utilities, training utilities, and we're going to start Tensorboard, which is a tool for part of the TensorFlow release, which lets us kind of monitor the progress when we train a model. So initially there's nothing to see because we haven't done any training, but we get this nice embedded Tensorboard interface right in the notebook. Now we're going to do our first network, and we're going to sort of just naively make the simplest possible neural network to solve this problem. So all we're going to do is have two layers. The first layer is going to take the input digits and flatten them. So just turn them into bit strings, where each bit is represented, or each I should say pixel of the image is represented by 1 byte from 0 to 255. And that's because, as you saw earlier, these are black and white images. That's going to represent how dark a given pixel is, like where it is on the scale from completely white to completely black. And we're going to connect these input nodes to 10 output nodes. And we're going to specify an activation function for each of those output nodes called softmax. So really what we're doing here is building the simplest possible model to take all of the pixels in a given image. So 28 by 28, I'm not remembering what that number is, but hundreds of pixels, 600 or something. Somebody will help me in the chat. And wiring every pixel up to 10 output nodes. And each of those output nodes is going to give us a probability for whether that pixel string, that long pixel string, 628 or 528, represents a 0, a 1, a 2, and so on. Now, the tool we're using to write the model is called Keras, which is an abstraction layer that runs on top of TensorFlow. I like it a lot because it hides a lot of the complexity you might face if you wrote native TensorFlow code. And it's become a very popular way to build neural networks and other machine learning models. So what we do here is we set this strategy, which is really just kind of a utility function that's written in one of those cells above, where it kind of sets in, you can think of it as an environmental setting in terms of how it wants to optimize the model and how it wants to, what the learning rate should be and so on. And then with this strategy, we have the actual definition of the model. That's what this model equals tf_keras.sequential is doing. We pass it a list of layers. And so the first layer says flatten with the input shape being 28 by 28 by 1. And the second layer is densely connected. That tells it every output from the previous layer should connect to this layer. And this layer should have 10 nodes, and it should have this softmax activation function, which, if you're not familiar with that, it's just a mathematical function for deciding when to consider an output as being significant based on its value between 0 and 1. So what I like about this is that we specify the model in kind of a declarative way. We say, I want this layer with this set of characteristics, and then I want this next layer. It's almost like drawing the model with code. And this model statement here ends here. So the really only thing we're passing it is this list. It's a list of layers, right? And that's kind of a nice way to think about a neural network anyway. So once we've defined the model, we compile it, and that kind of lets Keras turn it into an executable object that it can then start training. And then we call this train function, and we just name the model good because that's it's our first try. As I said earlier, it's a very naive approach, but maybe good enough for starters. We pass it the model, the strategy, and the batch size. So go ahead and run this cell if you would. And you'll see kind of a description of the model here. As we've talked, okay, 784 was the magic number. And we've flattened the first layer, and we have a dense connection to the second layer. And as you can see, there are 7,850 parameters in this model. Which makes sense because we have 784 times 10, and we have 10 more for the parameters for the output layer. So now it's running the training, and you should be seeing something like this where it's kind of going through these 10 epochs. I'm on number 6 at the moment, or 7 now. And while that's training, I got no dashboards are active for the currents after executing the start Tensorboard part. Yes, so you should see no dashboards are active, and that's because we haven't done anything with Tensorflow yet, or Tensorboard yet. We've just kind of set it up. So that is normal. And Amal asks how to choose the number of hidden layers in a neural network. That's a good question. And I don't have like a simple way of answering that because it tends to be one of these experience-based choices. So you'll tend to get a feeling for how many layers work well. But as far as I know, there are no like magic rules to know how many hidden layers and also how many nodes in any given layer. Trial and error and experience are generally the best answers for that. The other answer is, as I mentioned in the talk, there's this thing called AutoML, and that's worth using because it lets the computer figure that out, figure out the best architected network for you. I mean, it's good to play around with Keras and do this kind of exercise, but I think AutoML is great because it takes a lot of those questions out of the picture. So we're done training, and we have we can look at the loss and the accuracy, and it looks like we have training accuracy and validation accuracy, and I think we'll focus on the validation accuracy because that gives us a better sense of how good the model will be and when it's live. And we got roughly 94% with this naive approach, which isn't bad, but it's not good enough for a serious application that would be using this model. So the next version we can do is what I call better, which is to use multiple dense layers. So by adding a sort of a cascade of 3 layers and giving the hidden layers a different activation function called ReLU, reticulated linear unit, something like that, we tend to get a better result. And because we're, I think, a little short on time, I'm going to skip better, but I invite you to try it on your own after the talk. But let's jump to best. And best is going to add convolutional processing and regularization. I suspect many of you know those words, but if you haven't seen it before, convolution is a way of having the model kind of sort of scan the images one frame at a time. So it's taking into account the surrounding pixels when it's looking at any given pixel, which gives it a much better set of information with which to make decisions about. And regularization has to do with how it combines the outputs from a given stage in the network. So this is sort of the best model I could make with this with Keras. The difference that you'll see here, it's just like before, it's a sequential model with a list of layers, but now for each layer we've got like 3 steps. We've got this conv 2D, and that's saying I want a convolutional layer here, and when we do that we specify a kernel size. Then we do something called batch normalization, and that's sort of taking the data from each scan and combining it in some way to sort of reduce the amount of inputs at each level. And then we specify the activation function as we did before. So we have one convolutional layer, then we have a second convolutional layer, then a third, and then we flatten the output and send that into a dense layer of 200 nodes, do something called dropout, and then we do one last dense layer with 10 nodes. So this is the best network I could create, and it's on the order of 6 layers. And one of the key things that's happening here is that in the previous version, we simply flattened the input. So what that means is we took these 28 by 28 pixel images and we stretched them out into one long string of pixels. And now for the first time with the convolutional approach, we're not flattening the input anymore. We're giving the input as 28 by 28 images. So the network is able to see the sort of the surrounding pixels, as I said earlier, and it gives it much better information. So let's try training that. Click here. You can see it's calling it best, but it's using the model that it built up here. And this will take a little longer, but it's not too bad because it's using a GPU. But while you're waiting for this model to train, I want to go up to the top and call your attention to a link here. Learn TensorFlow and deep learning without a PhD. A lot of the stuff I'm talking about, I'm glossing over. I'm saying it really fast, like dropout. I just mentioned dropout, and I didn't tell you what that means. I kind of waved my hands a lot about regularization and softmax and ReLU. So I'm going through this at a very high speed because I just want to kind of give you a sense of how you build these networks and how you can run them once they're trained. But I strongly recommend this Learn TensorFlow without a PhD resource because it'll explain everything I'm kind of glossing over here. Let's go back to see how our model's doing. Bring this down a little bit. Okay, so now with all those layers, we have 354,000 parameters. And so that's why this is taking longer. But even with that, thanks to the GPU, we're about 60% done. So let's let that last bit finish. And if we look at the accuracy, we can see it. The naive version was 94% or something like that, 93%. We can already see this is doing much, much better because we're seeing validation accuracies of 1 and training accuracies in 0.999 region. Okay, I'm on my last epoch. Training accuracy is almost 1, 0.9998. And the final validation accuracy is 1.0, which seems unrealistic to me, but I think there probably is not enough data to get a more reasonable, more realistic estimate of the actual generalized accuracy of this model. But if you go to the next cell, save model and prep for use by TensorFlow JS, go ahead and click save, or click that cell. And what that's doing is writing the model out to disk so that we can pull it into and run it in this notebook. I want to actually run it interactively in this notebook. So once that's done, click the next cell. And what this is doing is converting the model to the right format and giving us a little cloning a Git repo that I wrote that's going to give us the ability to draw and kind of interact with this model right inside the notebook. So run that cell. You can see it's doing a pip install, converting the model for use by JavaScript. And it's JavaScript because we want to run this using web capabilities inside the notebook. And that's done. So now let's run some interactive tests. So scroll down to this cell that says run this cell to launch the canvas. So we run that. And what you should see is this. It should say loading model. And eventually it should finish loading and that loading model sign should go away. Let me make this full screen. And what this is doing now is it's going to watch what you draw. And it's going to send, as you're drawing it, it's going to continually send the image to the model you just trained. So as I draw this, and it was doing the real-time guessing, but I couldn't see it because my screen is so big. So let me pull it, make it smaller so you can see it working in real time. Okay, so if you click clear, everything gets wiped out. And let me do it again. Here's a 2. And what's kind of fun about this is you can see it figuring out. It thinks it's a 1, and then it gets that it's a 7. But if I kind of come down here, it starts to get a hint that maybe it's a 3. And then as I do this, it can see, okay, yeah, that's a 3. So you can sort of almost see the model thinking as you're drawing, which is kind of cool. So that is really the sort of the finale of the exercise. I hope that worked for you. But as I said, you saw nothing about Vertex. That was really just a basic machine learning capabilities kind of a thing. How would I have done that all using Vertex? And I'll just summarize very quickly because I had promised an hour and a half and I'm already an hour and 3/4. So what I would do is here when I got the data, so this tfds.load, I would put the data into a managed data set, and then I would share it with my team and we could fine tune it, and we would have one set of data that had one source of truth that we could all work with together and refine together. These utility functions might be part of some code that I would write to be a custom training object. And then I would upload the custom training. So this code I would upload to the cloud. And instead of manually running it in a notebook or on my laptop, I would run it in the cloud. In this case, I could run it on a laptop because it's not a very sophisticated model. But if it was a really big model or a lot of data, like really big data or both, I would really want to run it in the cloud for all the reasons I talked about earlier. So I would upload this model code to the training, Vertex AI training that I showed you. And then I would be able to make predictions from the cloud. And so just as I'm sort of doing predictions behind the scenes here locally, but I could just as well make the predictions from a server in the cloud. And the great thing about that is if I release this as a service and everybody in the world suddenly started using it, it would automatically scale. Whereas if a lot of people started using this version running on my laptop here, it would fall over. So you get the automatic deployment on the web for anybody that wants to use it publicly instead of being limited to a notebook, and you get the automatic scaling with Vertex. But as I said earlier, I think if there's interest, I'd be happy to come back and do a version of something like this where we use all the Vertex capabilities instead of just running in a local notebook. Just checking questions. Did I do anything with?
Yes. So
just checking to see if anything interesting happened with Tensorboard.
Okay.
Yeah, I'm not seeing. I have a feeling the Tensorboard part is not working, but I don't want to try to debug it in real time. So I see a question about how to tune hyperparameters, and that's sort of similar to the other question in the sense that there's a lot of trial and error to do that. There are some packages that can simplify the tuning, and in particular, Vertex has something called Vizier. And Vizier's job is specifically hyperparameter tuning. And so I highly recommend taking a look at Vertex AI Vizier. That's a Vizier. It's specifically built for this question. And can we export our model as a TF-Lite file? And yes, I haven't done that myself, but I'm pretty sure that you can because I've already exported it to a different format to run it in to the JavaScript format to run it here locally in this notebook. So I apologize for going over. I hope that was fun. Hope you got a chance to get a good sense of what Vertex AI is all about. And yeah, thanks again for having me.
Yeah, thank you so much for your time, and thank you all for your attention. Yeah, that was so great.
Thank you very much, Marc, for accepting our invitation.
Yeah. So
thank you for having me. And one last thing I'll mention is if I can help anybody, if you have questions that you didn't think of or didn't want to ask during the live talk, my email is mco@google.com. Feel free to reach out if I can help you with anything.
Yes, so we leave the email in the chat. Fine. Okay, thank you all for attention, and don't hesitate to join us on our meetup group to be notified about our next activity. So we leave some links in the chat about our next meetups. And yeah, goodbye. Great. Bye all. Thank you.
Goodbye.